Now, before I do talk about the homework on section 6.4, I forgot to mention last time that there's a small mistake in your book on page 585, which I also typed out in the notes beneath the video, that the Taylor series chart for natural log 1 plus x is, here's where your book has it. Let's see. Okay, natural log, see, it starts at n equal to 0. The natural log doesn't start at 0. It starts at 1 because, well, being that it divides by n, if n is 0, you're going to have a problem. But luckily, the first term is 0, so we can just ignore it and then start the counting at n equals to 1, and they'll work out. So for homework of this section, in the previous video, I mentioned the homework, and then I clicked the wrong button and the video stopped. So I will repeat the homework, which I have finished by now. So it is for homework, page 596, please do problems 175, 77, 79, 81, 85, 89, 95. Yeah, 95 has a slight typo. You have to, it says 4x, but it actually just means x, and that's what the answer gives. See, that's why I realized that. Anyway, keep going. 197, 201, 3, 5, 7, 9, 11, 15, 17, 19, and then 41. And problem 41, the answer in the back is slightly wrong. I mean, part of it is wrong. I believe, and I'll show you in a moment why I think so. And then finally, 245. So please go do your homework, and when you're done, I want to talk about them. Now that you're done with the homework, let's look at some of the problems. Now, so far, the first few problems are all straightforward. You don't even have to write stuff out. You just follow the formula and plug it in. Okay, let's look at problem 175. We have a problem where we have 1 plus x squared to the power minus 1/3. How would you do that? Well, you just plug it into that formula for binomial expansion of things that has a power that isn't a positive integer. Now in this case is a minus negative fraction. You plug it in anyway and write it down. That's your answer. And when I say that, I'm referring to this formula right here at the bottom of the chart on 585, page 585, where you have well, see, the 1 plus x to the power r is that r choose n, x to the power n, from n added from 0 to infinity. And that's the formula we're going to be using for the next few problems as well. Now the next thing we're doing is, okay, 177, see? The exact same thing. You just plug in the proper formulas. R goes on the top of R choose n, and write everything down as is. The answer of the book might be cleaned up slightly. You know, they take the negative 1 out and stuff like that. But generally speaking, that's good enough for me. In fact, that's even shorter than if you pull the negative 1 out. Next, 180, I think 179, I did it down here. I'll do 181 first. Okay, now 181, then same thing, except there's a trick here. Now, like I said, the formula has to look exactly like 1 plus x. Okay, if it doesn't look like 1 plus x, see, the original formula says 1 plus x. If it doesn't look exactly like that, then you have to beat it around until it does. So let's see, what are we doing? Okay, 181. So being that 181 doesn't look like that, there's no 1 plus anything here, there's a trick you can pull, as the book shows you. Okay, the trick is, here's the trick in the hint. So you follow the trick. So now the negative x minus 1 squared becomes the new x in the formula. So you plug that whole thing into the x, okay, shove it all in, and then apply the formula and maybe clean it up a little bit or not. Well, you know, that's good enough. So then a couple lines later, you got your answer. Next, let's look at 179. What is that? Yeah, same thing. What you have to do in this case is your formula has to be in the 1 plus x format, but this isn't 1 plus x. There's a 2 there instead. So you need to pull the 2 out, okay, and factor the 2 out with algebra tricks, and then everything will look like the 1 plus x format. then in this case, you're doing 1 plus x squared over 2. So you take the entire x squared over 2 and shove it into where x used to be, and then that's your answer. And that's good enough for me, okay? The book changed it a little bit to make it, I don't know, make it the way they like it. But I like it this way. This is good enough for me. So anyway, next, 185, same thing. You only have the square root of x. X equals 9. So how are we going to do that? I guess we are just going to beat it into something that looks like 1 plus x. So if you do this, and after some manipulation, you realize this is the same as x. Okay, 1 plus x minus 9 over 9 is just x. Once you know that, then you again put x minus 9 over 9 right into the x position, and then come out with this formula right here. And that should be the right answer. Next, let's look at problem 195, where, as I mentioned earlier, you have to replace the 1 plus 4x with 1 plus x. Otherwise, you can't get the answer at the right back of the book. Now, if you have 1 plus x, then here's a trick. I mean, instead of expanding at r equal to 4/3, you pull one out, factor one out. So what you have left is 1/3, and then you expand it at r equals to 1/3, which works much better. And then after you do the expansion, then you need to multiply it out. That is, multiply your infinite series, your Taylor series, with 1 plus x. You do it by doing just the first few terms, and then call it good enough. Okay, and so yeah. So next, let's look at problem 197, which we have this polynomial that again isn't in the form of the binomial expansion. Remember, the binomial, we need 1 plus x. That's it, okay? If it's not in the form of 1 plus x, we can't use the binomial expansion. Okay, there it is. So then so we need to pull out a trick to make it look that way. And here's so the book provides a hint, a convenient little hint. So what you do is that you will turn it into this, and at the same time, you also satisfy the requirement that a equals to -3. So you're expanding it as x minus 3. Okay, that's expanding it at 3. And then you turn this thing into this format, which comes out readily after you complete the square. And then you plug in the formula that's already given by the book. The book is very nice. You don't have to, do all that fraction yourself. The fraction's already done for you. So you just plug it in, and there is the answer, and that is correct. So next, let's look at problem 201, where you're supposed to do something like this. Okay, you're having this binomial expansion. This time we're not doing Taylor series. This is just your some average finite binomial with a positive integer for the power. The problem is that they want you to calculate what? The 99th derivative. In fact, they also want you to calculate it at 0 when x equals to 0. But the book didn't forgot to mention that part, but that's the purpose, okay? Which is fine. Which we will do that, okay? So if you write it out, the first few terms, I wrote out the first 2 terms. We have fx, so it's x to the power 100 plus something x to the power 96, right? And so what happens when you take 99th power? Well, if you think about it, the first time it's 100, the second time it goes to multiply by 99, it's very likely to be 100 factorial times x. That's the 99th power, okay? Because all other terms, when you take something like this, x to a 96 power 99 times, and taking derivative 99 times is going to be 0 before you get to the end. And that's true with all the rest of the terms, which are going to have power that's less than 100. So all those are disappeared. So then you have just x to the power 100. Now, but this is, I'm just sort of guessing it. To be absolutely clear, I wrote it out, see? Because you write them out. So the first f prime of x, first derivative is 99 times 100. Second derivative, 98 with 100 times 99, right? And so eventually you figure out a formula. The nth derivative is x to the power 100 minus n times 199 all the way down to 100 minus n plus 1. Okay, and this n works if you plug n equal to 2 to test my formula. So it does work. Therefore, the 99th derivative really is 100 factorial times x. It's 100 multiplied down all the way down to 2. So that's 100 factorial. Now, we don't need to know what 100 factorial is because it's too big for your average calculator to handle. The average calculator can do something like 70 factorial. Then it ran out of something. The number is too big. So then what we have is so then what the book doesn't say is they want you to calculate x as 0. So after we did all that work, we plug x equal to 0, and the whole answer is just 0 anyway. All right, but it's still good to see how you might do some big problems, such as taking the derivative 100 times, and it turns out to be not so bad. Okay, because yeah. Anyway, so next, let's look at problem 203, where we are supposed to develop the Taylor series for 2 to the power x. Now, the Taylor series formula originally is on page 563, but basically what it is you have a function. The series goes as you have the function, the derivative, second derivative, divided by the factorial of said derivative. In other words, if it's second derivative, then you divide by 2, third derivative, divide by 3. So it's fairly easy to remember. However, you should, I always like to look up the formula if I haven't seen it for a few hours or something to make sure that I didn't miss anything. Because these formulas are long and complicated, you know. You want to get it right and not miss a little bit. Because if you miss a little bit, you're off by a mile. But anyway, so that's the formula. So we are going to follow the formula by, well, taking the derivative. First, the derivative of b to the power x in the differentiation formulas is bx natural log of b. Okay, in case you forget this, you can look this up as 706. Now, knowing that, then we take the derivative, and you notice that the derivatives comes out pretty nicely because, well, b to the x is similar to the e to the x, the e function. It's just off by the natural log a little bit. So its behavior is somewhat similar, see? So the nth derivative is 2 to the power x is itself, except that it has to multiply by natural log of n. Now, in this case, we're developing the Taylor series around at 0, x equal to 0. So that is, so 2 to the x becomes 1. So the f prime at 0 is just natural log of 2 to the power n, accordingly. As a result, you can write down the formula, which looks like this, okay? And eventually, we get something like that. And that is the right answer. Now, at this point, I decided to develop the formula for b to the power x, which the book didn't do, but I thought it might come in handy. Who knows, right? So similarly, if you replace b with, replace 2 with any general positive number such as b, then I get this formula too, okay, which is similar, almost identical to this one, except for the b. And then you notice that this formula is very similar to the e to the x Taylor series, right? The only difference is you have to multiply it by a bunch of natural log of b's to the power n. That's the only difference. Now, the natural log it converges for all numbers. The range of convergence is very big. That is for all x. Now, what about this one? So I tried it by applying the ratio test. So when you apply the ratio test, and then a ratio test works really nice for this type of thing because stuff cancels out a lot, right? So all you got is natural log of b times x, which as n goes to infinity, now natural log of b and x are both fixed numbers for this. Okay, only n goes to infinity. These things, they might be big, but they don't go anywhere. So as n goes to infinity, this thing's going to go to 0. For all x, which means this series converges for all x. Yeah. So I took a screenshot of the book's chart, 585, I think it was, and then I added b to the x in there. Okay, just for the, I don't know. It might not be useful, but it might be. As you notice the interval convergence, remember that e to the x, sine of the x, and cosine of x, these three things are the only things that converges from infinity to infinity for values of x. The reason for that is, if you look at it closely, is because they have factorial in the denominator. Okay, and as you remember, factorial grows fast. Okay, by 70, it's already blew your calculator. You can't do it anymore. So that's why anytime they have a factorial, eventually the series converges everywhere, because the factorial is just killing it. All right, so that's problem 203. Next, let's look at 209, where we have to do f of x equal to sine square of x. Now, the first thing you might think of is to do sine squared. We don't have a formula for sine squared, but we do have a formula for sine, right? Here's the sine function. So let's take this thing, and then we'll multiply the infinite series with the infinite series, like we have learned to do that at some point. I mean, a few lessons ago. And then come up with it, which you can do, but luckily we have the book gives us a nice hint, okay, so that we can avoid doing that, because multiplying infinite series with infinite series is not as much fun as it sounds, because you have to do it infinitely, right? So but luckily there is a trick that we can avoid doing that. So we rewrite sine squared as some kind of cosine without squared, okay, cosine 2x. So then we will work on it that way. And to do that, first we write down the cosine formula, which is in that chart I just showed you. Actually, I will show it to you again. See, here is the cosine formula, which we did in one of the examples. Okay, so let's copy that thing down. And then next we're going to plug in the formula as it says. So sine squared equals to 1/2, okay, minus 1/2 of this pile of stuff, where you stuff 2x into where x used to be. So here's 2x right there. And then, and that is basically the answer. However, if you look at the back of the book, the answer doesn't look like that. The reason is because the first term of this thing happens to be 1/2. So you have 1/2 minus 1/2. Here's another 1/2. Actually, I think it was 1. Anyway, the point is, you end up have 1/2 minus 1/2 for the constant term, so it becomes 0. So the actual answer, you can just write it as starting at 1. That's why that's the difference. That's why this looks different from this, but it's actually the same thing if you start it at 1. So that is the right answer. Next, let's look at problem 215, where we integrate cosine of square root of t. Well, we're just going to integrate it term by term and hope that everything converges. Actually, in cosine's case, cosine tends to converge very nicely because it has a factorial at the bottom of the Taylor series, so then everything works out. And therefore, you just go ahead and perform the integration, blindly, like you always do. And then just do the integration of the polynomial, okay? So, which is very straightforward, and come up with that, and that is the answer. Next, let's look at problem 217, where we have another function. What is that? We don't care what it is. The point is we're supposed to integrate it, and we will. So you just stick it in there and then integrate it term by term, which quickly comes to here, right? And then you evaluate it at x minus evaluating at 0. Well, at 0, this thing happens to be 0, so we can ignore it. So at x, this is it. Now, and then we're going to change it a little bit, start counting at 1. Okay, and we'll change the index system. So instead of n plus 1, a bunch of n plus 1s, we're going to change it to just n, so that it looks neater. And then the negative 1 can move it a slot. Is n plus 1 or n minus 1 the same thing, because it's negative 1. And that is the right answer. Next, let's do problem 219. We have to develop the Taylor series for tangent x. All right, well, how do you do that? Well, you just follow the formula, and let's take the derivative to about the 5th position. And here's what happened. See, the first derivative went pretty nice, and f of 0 is just 1. The second derivative is still not too bad. f is at 0, f double prime is just 0 because tangent x is 0. And the third derivative is starting to look kind of annoying, but it's still okay. And the value is 2, okay, for x equal to 0. The fourth derivative is getting a bit hard. And I did it with the derivative calculator, which I have in the video description. Then finally, so that ended up being 0 as well. And finally, the fifth derivative is I'm not even going to write it down because it's quite tedious. Okay, it goes on. So I plugged it into the derivative calculator, and out comes this big long answer in which, remember, secant equals to 1 and tangent equal to 0. So with that makes it slightly less annoying. So the fifth power, by the time I got it all done, then see, that's the fifth derivative. I skipped writing it out and just figure out what's the value at 0. It ended up being 16 or something. 16? Why is it equal to 16? I'm not sure. Let me check. Actually, it's right. It is 16. And then let's plug it back in. Okay. Now plugging it back in, then remember you have to divide it by the various factorials. And after you have done that, then it ends up being these three things that we've gone through a lot of work to get. And that is the right answer at the back of the book. 229, we are supposed to do the radius of convergence for the Taylor series. So let's, for natural log of 1 plus x squared, so let's do that. We'll take the original formula of natural log and then plug x squared in place of x. Okay, now remember that, as I mentioned earlier, that for the natural log, n's need to start at 1. Okay, because if you start n at 0, it wouldn't make any sense because n is at the bottom and notice of the fraction, and you'll be dividing by 0, which is not acceptable. So remember to start at 1, not 0. And that equals to something, you really don't even need to write it out. Next, let's do the ratio test. And the ratio test for power series always comes out nicely, basically, right? And you just have to see when is this thing less than 1? That will give you the radius. Well, as n approach infinity, n over n plus 1 becomes 1, because as n approach infinity, n and n plus 1 are not that different, right? So there's a standard way of solving that limit. You divide everything by n. Divide the top by n and the bottom by n. Let n go to infinity. That will give you the answer of 1, which means that by the ratio test, the absolute value of the x squared has to be less than 1. So x is less than 1, and 1 is the radius of convergence, which is correct. Okay, next, let's look at problem 241. So problem 241, we have a power series and then a differential equation, which is, in terms of power series, the process is tedious but doable. And it's not that bad either, actually. So we have our power series, right? And here's the power series, the differential equation with all the initial conditions here. So what are we going to do? Well, we're going to take the derivative and see and line up stuff and calculate what the coefficients are for our power series. So I did that, right? I wrote it out, and then I came up with something that is similar, but the opposite signs. Like I got negative 1/6 for A3, or some of the, and then negative 1, I think 1/2 for A2, but the book gave a positive value, same number but positive, or something like that. So then I redid this problem. Okay, we're also supposed to write down the recursive formula for A. So to do that, you calculate what is xn, following the pattern, and you quickly notice the x to the power n is n plus 1 times n plus 2 of an plus 2, etc., all this stuff. And then when you plug an plus 2 out, you get this. Okay, and that can be re-indexed to look like, here's what the book has, here's what I have. They're the same thing if you re-index it. That is, you let n be the new n plus 2. And if that's true, everything bumps back a step or two, and then it's the same. This is the same formula in the sense that it gives you the same answers. Now, and when I did that and I plug it in, the answer is still the same. That I got a negative value. See, the A2 is negative 1/2, and then A3 is negative 1/6. So at that point, I decided that it's reasonable to believe that the book is wrong in that part. But they did get the recursive formula right. And but even then, I can't get the answer they have. When you plug in the values into the recursive formula, I get A5 is positive. Okay, I think they have negative. So, but I believe that my answer is correct. But overall, that is how you solve a differential equation with the help of power series, which is kind of neat because those differential equations are harder than heck to solve. Okay, otherwise, this way you're actually able to come up with an answer, even though the answer is in the form of infinite series, which is you have to worry about convergence and stuff. But overall, at least that's something. You do have an answer, so that is nice, and that's an answer to an extremely tough question. The last problem I want to do is number 245, where we're supposed to calculate the integral of these things. Okay, let's do it, right? Okay, so to calculate the integrals, we will do, well, as always, okay? We plug in here's the cosines formula for Taylor series extension. We are going to plug the t in there, right? And then go ahead and integrate. And that will, the integration comes out right away because you're just integrating polynomials. So you can integrate all of them at the same time. And then you evaluate it at t equal to x and t equal to 0. Well, t equal to x t equal to 0 happens to be 0 because, well, if you look at it, you'll realize why. So then when t equal to x, then we get this thing right here, which is good. And that is the answer, I believe. So when you have only 50 terms, then you rewrite it as n goes from 0 to 50 down here. Now, similarly, I also wrote down the value for sine of x, but unfortunately, I wasn't paying attention. I forgot that we're supposed to do 2t, right? Yeah, it's 2t. I forgot that and wrote down only t, and then I messed up and had to scratch it out. So that's why it's all scratched out there. But eventually, I got myself back on track and got the right answer and calculated in the same way the sine of x, s of x equals to this thing, and end up with a similar thing as the c value, which is 4n plus 3 over 4n plus 3. X to the power 4n plus 3. And otherwise, the situation is very similar. It's evaluated as 0 is equal to 0, so you don't have to worry about that. So I did the integration, and that is what I came out. And then the book wants you to graph this thing from what, 0 to pi or something, 2 pi, something like that. Yeah, 2 pi. All right, so I graphed it on the Desmos calculator, and I just typed it in, right? See that thing? Y equal to sum. Yeah, that's how you type it into the, you don't even need to use any special part. Just type it into the normal Desmos graphing calculator. The way that is, remember, the summation sign is done by typing the letters SUM, and that will give you the summation sign. Type every other thing out. See, the red line is, I don't know, cosine. Yeah. And then the blue line is sine. And look at how hot it is. It just looks so beautiful, right? It's just all nice and smooth. Yeah. And they look similar. They're just a little bit off, just like normal sine and cosine. These things are just slightly off, and then towards the end, they kind of go nuts. But until then, things look beautiful. See? Yeah, it looks beautiful till the end. So that is calculated at 50, and that marks the end of this section. And I think, yeah, this is also the end of this chapter. So now so far we have done quite a bit of hard work, but the next chapter is going to be the parametric equations, which are much easier. Okay, so we'll have a relaxing time towards the end of the calculus 2.